Well, my dear students, in continuation to the last class, today let us discuss about the various relative positions of circles comparing to a point, comparing to a straight line and comparing to another circle here. Especially when a point is given in the plane, how to find out its relative position comparing to a particular circle given. Let us see how to analyze this one. For example, we are imagining a circle S equals to 0. Just randomly we are choosing a circle in the plane S equal to 0, whose center is taken as minus g comma minus f and radius as r, where we know that r equals to g square plus f square minus c under root and center is minus g comma minus f. Now let us imagine a point p x1 comma y1 somewhere in the plane of the circle given, maybe internal or maybe external, maybe lying on the circle also. Let us see how to find the position of this one with respect to this circle. Directly from the diagram we can analyze that distance from center to the point P, if CP is greater than the radius, it is indicating that the point is external to the circle. Suppose CP and R both are equal, clearly the point will come on the circumference somewhere, means it belongs to the circle. If it is less than R, obviously the point is inside. So we can locate the position of a point with respect to a circle by finding its distance from center to that particular point. If that CP value is more than R, it is external, equal to R on the circle, and less than R, the point is internal. Instead of finding this distance, we can also find out a mechanism to find the same in better way by using simple calculations. Instead of comparing CP and R, let us compare CP square and R square. We are getting the same relative positions in this case also. If CP square greater than R square, transferring left side, CP square minus R square will become greater than 0. So here, instead of finding CPR or CP square or R square, we can get the relation for the same by finding CP square minus R square. This CP square minus R square quantity is particularly defined as the power of the given point with respect to the given circle. This can be named as power of the point P x1 y1 with respect to the circle here. What is the use of this power and how to find out this power? Let us calculate this one. CP square minus R square equals to distance between 2 points x1 plus g whole square plus y1 plus f whole square minus R square g square plus f square minus c. If we are simplifying this one, we get x1 square of the second term y1 square plus 2g x1 plus 2f y1. In this g square, in this f square, minus g square f square both are cancelled, minus of minus plus c. But already we have discussed this one as the notation S11. So the power of a point with respect to the circle can be calculated as simply S11, the value which is obtained by substituting the point in the circle equation. So here S11 is taken as the power of the point and S11 will decide the relative position of the point with respect to the circle. Here S11 greater than 0, you are getting CP square minus R square greater than 0, CP square greater than R square and CP greater than R. So the point is external to the circle. In similar way, S11 equals to 0, the point lies on the circle, less than 0, the point will be interior. Here, this is outside, this is on the circle and this point is interior. So S11 clearly has the power to decide the relative position of the given point with respect to the given circle, and hence we can just take this pointer, this value as power of the given point with respect to the given circle. So power can be calculated by using S11. Simply the given point is substituted in the circle equation. Whatever the value obtained will decide its position. Positive outside equals to 0 on the circle and less than 0 interior. Now, if you analyze the range of power of a point with respect to the circle, here Cp square minus R square is power. Cp range, if you analyze, as the point is coming closer to the center, when the point P is coinciding with the center, Cp will take the least distance 0. In that case, 0 minus R square will give you the power in that particular case. That is why here S11 range can be taken as least value is minus R square, which is taken for the center of the circle. As the point is going away from the center, because there is no limit to this extension, that's why it has no upper cutoff. Therefore, the power of a point with respect to circle takes the range from minus R square closed to infinite. This is the range of the given power we can decide. Now, we can decide the relative position of a straight line with respect to a circle, just like we have seen the relative position of point and circle in the previous case. Here, once again, we are imagining the general circle is equal to 0 in the plane somewhere, and a straight line, some Lx plus My plus n equals to 0 is drawn. To decide its relative position with respect to this circle, we can take three relative positions. One is the circle do not meet the straight line in real points, or if it is coming closer, the straight line may touch the circle at single point. This is the second case, in which case the line is called tangent to the circle. And if it is coming little bit lower here, the line will cut the circle in two distinct points, in which case it becomes a secant to the circle. Here it is tangent, and in the first case there is no common point between straight line and circle here. How to decide the relative position of a straight line with respect to a circle? To observe this one, here we start with the center minus g comma minus f, and as usual take the radius as r. In the diagram, if you observe very closely, the perpendicular distance from center to the given line, if we are assuming it as some d, if this d value is more than the radius of the circle, clearly the line has no common point with the circle, then line do not meet. Line do not meet the circle here. Next, if d value equals to r, the second case arises. Exactly this d value equals to radius of the circle we are getting, in which case line will become a tangent. So we can say that if a line is touching a circle, the condition is, necessary condition is, distance from center to that line is equals to radius of the circle. It is a very useful point in solving many points in various types of exams. And third case, if the value of d is less than r, then line is a secant line. In this particular case, line will become a secant line. Here, like this, we can decide the relative position of a straight line with respect to a circle. Three cases arises. D greater than r do not meet in real points. D equals to r, line is a tangent to the circle, which is a very important condition, second one. And the third one is, if d less than r, then it will cut at two distinct points. Now we can take a special case also, because it's most frequently coming in different questions. how to find the relative position of a circle with respect to the given coordinate axis. Axis also two straight lines, but because they are very specific straight lines, very frequently comes, that's why we can analyze it in a separate case also. Let us see those two cases also now. We are taking coordinate axis in xy plane. This is x axis, this is y axis. Now, if a circle is taken with respect to x axis, if we are analyzing the positions, relative positions of the circles, as usual we can take three cases. It do not meet x axis in real points, or it may touch, it may cut x axis in two distinct points, and the third case, it may touch x axis at one point, in which case x axis will be a tangent to the circle. Here secant, here it do not meet the case. Now, in this case, if you apply the previous conditions, if this is the center minus g comma minus f, the perpendicular distance from center to the x axis, as we know already, becomes its ordinate. This value is always called as its ordinate. That's why this ordinate is taken as minus f. To avoid ambiguity of signs, here we are taking modulus sign. And this is distance. Distance from the center to the line is mod minus f, and radius equals to g square plus f square minus c under root. If you are comparing these distances, here d square equals to f square and r square equals to g square plus f square minus c. Here, if d is greater than r, d square greater than r square, in this case d square f square greater than g square plus f square minus c. Here we can cancel f square and f square here, then you are getting g square minus c less than 0. So, if g square minus c is less than 0, d is greater than r, in that case, circle do not meet x axis in real points. There is no common point between circle and x axis. Similarly, g square minus c equals to 0, circle touches x axis. And g square minus c greater than 0, x axis cuts at two distinct points. Like this we can analyze very comfortably with respect to the axis. So, if g square minus c equals to 0, a very important middle case, then the circle touches x axis. G square minus c greater than 0, circle cuts x axis at two distinct points, and if g square minus c less than 0, circle do not meet x axis. Very sensibly the questions can be constructed on this particular points by mixing it with different various conditions in competitive exams. Okay. Here we will come to all those in coming classes while discussing the problems separately. Here, in very similar way, we can analyze the relative position of a circle with respect to y-axis also. One can guess very comfortably the relative position of a circle with respect to y-axis also in this similar way. If f square minus c greater than 0, y-axis cuts the circle in two distinct points. Just diagrammatically I am giving you the case here. If f square minus c less than 0, y-axis do not meet x-axis, and f square minus c equals to 0, then simply the circle touches y-axis. And simultaneously we can apply both of these conditions to see the relative position of a circle with respect to x-axis as well as y-axis together. Here, overall idea, if you check in all these cases, here if a circle is touching both the axes x and y axis simultaneously, here in this case we get the condition g square equals to c as well as f square equals to c. Then we get the condition g square equals to f square equals to c. Suppose if a circle is like this, it will cut x-axis as well as y-axis at two distinct points each case. In this case, g square is greater than c and f square is greater than c. Whereas coming to this circle analysis, here it is neither meeting x-axis nor y-axis. Hence we get the condition that g square less than c and f square less than c. Like this, various combinations of cases we can construct from the previous relative positions, which are very useful points in solving problems related with this type of conditions. Maybe given the conditions alone like this, or maybe mixed up with some other conditions which we are going to discuss in coming classes about this. Now we can also take the relative positions with other method also. If you want to check this second method, we take the help of simple geometry here. Suppose a circle with radius r units taken. If the radius of the circle is r and if it is touching x-axis, diagrammatically we can say that this length is also equals to r, which is also called the ordinate of that particular point. Perpendicular distance from x-axis can be taken as ordinate. So here clearly the ordinate of this center will be r. Now if it is touching, suppose y-axis, then its abscissa will become r. And if a circle is touching both the axes, x and y-axis both simultaneously here, then both of these will be equals to r, then center will become r comma r. By using this way also geometrically, here center coordinates will be always numerically taking r and r when it is touching both the axes, but depending on the quadrant in which circle is touching axis, these signs will be changing. For example, if this circle is touching both the axes in the fourth quadrant, then this abscissa will be positive and ordinate will be minus r will come. Similarly, in third quadrant, if it is touching, both will become negative, and here in second quadrant minus and plus combinations will come. That is why the general form of a circle touching both the axes can be taken with the centers in the form of plus r minus r plus r minus r, and radius can be taken as r. Now if you look at these four circles which are touching both the axes in various quadrants and having same radius r. Coming to the first circle touching both the axes in the first quadrant, the center taken as r comma r. The circle touching both the axes in the second quadrant will take the center minus r comma r, and the same in the third quadrant will become minus r, and in the fourth quadrant r comma minus r can be taken. Here all the centers are in the form of plus r minus r plus r minus r. Depending on the quadrant in which it is touching both the axes, we can decide the signs of this center abscissa as well as ordinate. We can also take one more important point in these four circles, observing closely. If a circle is touching both the axes in the first and third quadrants, the centers, if you have a close look, it is r comma r, this is minus r comma minus r. Here abscissa, ordinate both are equal. In this also abscissa and ordinate both are equal. So both of these points are satisfying the condition abscissa equals to ordinate. That is why both of these points are lying on the line x equals to y, which is angular bisector of the first and third quadrants. So if you are joining these 2 points, we are getting the straight line y equals to x. In very similar way, second quadrant and fourth quadrant, if you observe, circle touching both the axes in second and fourth quadrants, and the center abscisse ordinate, if you are analyzing here, r minus r, here minus r plus r, both are numerically equal but opposite in sign. That is why here we can take the condition for these 2 points satisfied by the relation x equal to minus y, or minus x equals to y, which is nothing but the straight line x plus y equals to 0, which is representing angular bisector of these two axes in second and fourth quadrants. Hence, we can conclude a valid point here that if a circle is touching both the axes in any of the axes, obviously the center lies on the angular bisectors of coordinate axis. That is, x plus y into x minus y will become x square minus y square equals to 0. In particular, if the circle is touching in first and third quadrants, it lies on the line x equal to y, and if it is touching in fourth and second quadrants, centers lies on the line y equals to minus x. This point is a very valid point for solving many problems in a very sensitive way, and that too in complete shortcut approach. We can use this point for solving many types of questions. We can construct different sensible questions based on this simple point. We can discuss a small example based on this simple concept I have given. You can get an idea overall how we can do the problems by using this simple point. Let us see the example based on this. According to the given problem, here two circles touching both the axes and intersecting at the point 1, 4. As per the given problem here, two circles touching both the axes are intersecting at the point A 1, 4. Now, we have to find out the other point of intersection, length of common chord, line joining their centers, equations of these circles both, etc. Various types of problems we can solve very comfortably by using previous concept. If you look at these two circles, both of these circles are intersecting each other at two distinct points, A and B, and also these two circles are touching both the axes in the first quadrant. So, according to the previous analysis we have taken, we can say that clearly the centers of these two circles are lying on the line y equals to x, because clearly the point is lying in the first quadrant and obviously the two circles are touching both the axes in the first quadrant. So, the center can be taken on the line y equals to x. Here, we know that both the centers are lying on the same line y equals to x. Suppose this is C1, this is C2. Centers of the given two circles taken as C1 and C2. Line joining centers is y equals to x. Next, if we join these common points of the circles A and B, this AB is called as a common circle, and from simple geometry one can guess that this AB will be bisected by this line of centers perpendicularly. So, this will become perpendicular bisector of the common chord of AB, in which case A and B will be images to each other. And we know that image of a point A comma B with respect to the line y equals to x is B comma A. That is why image of 1 comma 4 with respect to the line y equals to x will be 4 comma 1. So, we are getting the second point of intersection also as 4 comma 1. If A and B, both of these points you know, then AB can be under root 4 minus 1 whole square 9 plus 1 minus 4 whole square 9 will be root 18, nothing but 3 root 2 will come. So we could able to get the length of the common chord of these two circles, and also we got the equation of line joining these two centers. Now coming to the other one, if we want to find out the equations of circles individually, we require the radius of the circles. If you are taking one of the radii of the circles as some r, we know that the center will be r comma r. As per the analysis given just now, if you are taking the center of the circle touching both the axes as r comma r, here we know the center, we know a point on the circumference. That's why joining these 2 points, you are getting AC1 equals to obviously the radius. So we got a clear relation between r here and the given coordinates. Simplifying this one, on squaring both sides, AC1 square equals to r square. So we are getting r minus 1 whole square plus r minus 4 whole square equals to r square. After simplification, we get r square 2r square minus r square is r square, minus 2r minus 8r will be minus 10r, plus 1 plus 16 will be 17 equals to 0. So we can find out the roots of this. R equals to minus b plus or minus root b square minus 4ac by 2a. So 10 by 2 5 plus or minus 1 by 2 into root of 32 will be 5 plus or minus root 32 is 16 into 2. We can write 32 as 16 into 2. 16 under root taken as 4. 4 by 2 is 2. You are getting 2 root 2. Therefore, we are getting clearly two values for r. R equals to 5 plus 2 root 2 and 5 minus 2 root 2. 5 plus 2 root 2 will give you the radius of the bigger circle, and 5 minus 2 root 2 will give you the radius of the smaller circle. We know the radii of both the circles. Once the radius is obtained, center is nothing but r comma r. Therefore, we can get the equations of circles also by using center and radius form. Like this, with a simple point given for these two circles touching both the axes, common point, with the help of this common point, we can find out the line joining centers. We can find out the second point of intersection. We can find out the length of common chord. We can also find out the equations of both the circles touching both the axes satisfying the given condition, like this, by using radius of the given circle. So like this, we can do many problems very sensibly by using this simple concept of general form of a circle touching both the axes in different quadrants. We can take this as a very valid point for competitive exams.